Hello and welcome to this lesson in our study of linear algebra. In this lesson, we talk about quadratic forms, similar matrices, and how to diagonalize matrices and quadratic symmetric matrices. So first of all, let's talk about quadratic forms. Okay, so a quadratic form on a finite dimensional vector space Rn is a function defined on Rn whose value at a vector x, where x is also a finite dimensional vector, can be computed by expression of the form that q of x equals to x transpose ax, where a is what n by n symmetric matrix. Okay, so the simplest example of a quadratic form is given by x transpose ix. Okay, so now a quadratic form we can describe the nature of a quadratic form. Okay, so a quadratic form is said to be positive definite if q of x is greater than 0 for x not equal to 0. It is negative if q of x is less than 0. It's positive semi-definite if q of x is greater than or equal to 0. Then it is negative semi-definite if x is less than or equal to 0. Q of x is less than or equal to 0. And it is indefinite if q of x is both positive and negative. I hope it is clear. So now let's consider the following theorems. So if A is symmetric, then any two eigenvectors, please make this correction, it's not eigenvalues, any two eigenvectors from different eigenspaces are orthogonal. Okay, then an n by n matrix is orthogonally diagonalizable if and only if A is symmetric matrix. Okay, so now when you have A be a square symmetric matrix, it means A have the same number of rows and columns, and A is also the same as the transpose. Okay, A is the same as the transpose. A is equal to A transpose, and A is also what, a square matrix. Then the quadratic form q of x given by x transpose ax is positive definite if all the eigenvalues are positive. Okay, or if all the eigenvalues are what, greater than 0, then we say that the quadratic form is what, symmetric. Sorry, the quadratic form is positive definite. Also, the quadratic form q of x is negative definite if and only if all the eigenvalues of A are all what, negative. Okay, then it is positive semi-definite if and only if one of the eigenvalues of A is 0 and the others are positive. Okay, then it is negative semi-definite if and only if the eigenvalues of A is 0 and the others are negative. And lastly, it is indefinite if the eigenvalues of matrix A are what, both positive and negative. Okay, so you see that the quadratic form is what, indefinite. So let's look at some examples. Okay, so we let x be vector of two dimensions, that's x1, x2. Then we have to compute x transpose ax for the following matrices. So we have two matrices, okay, where the matrices are symmetric. Okay, so first of all, let's consider the symmetric matrix, the A. So since A is a 2 by 2 matrix, our vector x should be what, 2 dimension. Okay, so we let x be x1, x2. Therefore, x transpose ax is given by, so this x transpose, this A, then this x. When you multiply the vectors by matrix and we simplify, we get 4x1 squared plus 3x2 squared. Okay, also let's consider the second question. So we have symmetric matrix 3, negative 2, negative 2, 7. Then the X transpose AX is given by this. When we simplify this, we get 3x1 squared minus 4x1x2 plus 7x2 squared. Okay, we have another example. For x in R3, that's for a vector x of 3 dimensions, we have q of x is given by, or we let q of x given by 5x1 squared plus 3x2 squared plus 2x3 squared minus x1 x2 plus 8x2 x3. Okay, now to write this quadratic forms as x transpose ax. Okay, so first of all, you choose vector x such that the dimension of the vector x is what? 3. Okay, so we let x1, x2, x3 be the elements of vector x. So we let x, in other words, we let x be what? x1, x2, x3. Okay, then we form our symmetric matrix from this. So this is how we form our symmetric matrix. First of all, let's look at the diagonal elements. So we have 5x1 squared. Okay, that will be the first element in the leading diagonal of the matrix. And also have x2. Okay, we have 3x2 squared. That will be the second second element in the leading diagonal. Then we also have 2x3 squared. That's what we have here. Okay, then with the other elements, you see, let's consider minus x1, x2. Say that since it is symmetric, we divide the coefficient of x1, x2 by 2. Okay, and because it's symmetric, we can say that x1, x2 element in the, it means the what? Element in the row 1 column 2, and it's the same as element in the row 2 column 1. Okay, so we divide the coefficient of x1, x2 by 2. The coefficient is -1, so when we divide 2 by -2, we divide 2 by 2, get -half. Okay, -half. Then that will be the element of row 1 column 2 and row 2 column 1. So that's why we have -half here, -half here. Okay, then x2, x3 we divide, that's 8x2, x3, we divide it by 2, which gives us 4. Okay, so that will be the element in the second row, third column, and third row, second column. So that's why we have 4, 4 here. But there is no element in the first row, third column, and third row, first column. That's, there is no term of x1, x3 or x3, x1. Okay, so this is our matrix A. This is our vector x, and this is the transpose of x. Okay, so we have written q of x in the form x transpose ax. Okay, let's look at another example. So we have q of x given by x1 squared minus 8x1 x2 minus 5x2 squared. We have to compute the value of x for x. That's -3, 1, 2, -2, and 1, -3. Okay, so first of all, we generate our matrix A from this. So our A is given by 1, -4, -4, -5. Okay, and we can write q of x as x transpose ax. Okay, so when we consider the first vector, that's -3, 1, so the transpose is given by -3, 1, then matrix A 1, -4, -4, -5, then -3, 1. Okay, so we simplify this. When you simplify this, it's the same as substituting the vector x, that's -3, 1 into Q of X. When we do that, we get 28. That will be negative 3 squared, which is 9. The second term gives us 24, and 9 plus 24 is 33. Then the last thing gives us negative 5, which is 28. Okay. The same thing applies to the second vector and the third vector. I go through the process again, and when you simplify the second, I get 16. Then okay, so you can try our hands on the last one. So we have an exercise here. We let Q of x, y, z be equals to 3x squared minus 7xy plus 5xz plus 4y squared minus 4yz minus 3z squared. We have to write this in the form x transpose ax. So you can pause this video and try your hand on this question. So now we have quadratic form. So 3x squared, that's this, minus 7xy plus 5yxz plus 4y squared minus 4yz minus 3z squared. So we choose our vector x, such that x is given by this. Okay, x, y, z, and this is how we generate matrix A. So this 3 will be, we have 3, we have 4, then we have negative 3. That will be the diagonal elements. Okay, then the other entries, we divide each of them by 2. Okay, so minus 7xy, we divide minus 7 by 2. And then this xy, x represent the row number and y, that's the column number. Okay, so when you divide by 2, get negative 7x2, 7 over 2. Okay, so the negative 7 over 2, we place it on the first row. That will be the element in the first row, second column, and second row, first column. Okay, so we get negative 7 over 2, get negative 7 over 2 here. Then also have another term, 5x, we divide 2 by 2. Then we place it to, that will be the element in the first row, third column, and third row, first column. Okay, so we have 5 over 2 here. We also have 5 over 2 here. Okay, then we have negative 4yz. We divide negative 4 by 2, that's negative 2. And that will be the element in the second row, third column, and third row, second column. So we obtain our matrix A. Okay, so now we can write this in this form. So we have x transpose AX. Okay, I hope this is clear. Now let's move on to change of variables in a quadratic form. Okay, so when you have in a quadratic form, you can change the variables without any cross product term. Okay, so if x represents a variable vector in Rn, then change the variable in change of variable is an equation of the form x equals to pu. This is pu. Okay, or equivalently, u is equal to what? P inverse of x. So this simply means that it's a quadratic forms. Q of x is given by x transpose AX. Okay, so we let x equals to pu. Okay, we let x equals to pu such that this p is an invertible matrix and u is what? A new variable vector. Okay, and p, the columns of p are the normalized eigenvectors, okay, of matrix A, or they are the columns of p are the normalized eigenvectors of the symmetric matrix A. Okay, So we substitute x equals to pu into this. So when we do that, we get pu transpose a pu, okay? And this is the same as u transpose pu transpose a pu, okay? So, but we know that P transpose is AP is the same as a diagonalized matrix. So we let that one be D. And therefore, our quadratic form is now U transpose DU. Okay. So now let's look at some examples. So we let Q of X be equals to x1 squared minus 8x1 x2. This is supposed to be minus 5x2 squared, okay? This is not plus, make that correction. So we have minus 5 here. Okay, so our symmetric matrix A is given by 1, minus 4, minus 4, minus 5. Make that correction. Okay, this is supposed to be minus 5, not 5. So first of all, we find the eigenvalues of symmetric matrix A. Okay, so the eigenvalues of symmetric matrix A is given by A minus lambda I. Find the determinant of A minus lambda I is equal to 0. Okay, so when we do that, that will be 1 minus lambda minus 4 minus 4, then minus 5 minus lambda. Find the determinant, then we equate to 0. So when you solve this, you get our lambda 1 to be 3 and our lambda 2 to be negative 7. Okay, then we find the corresponding eigenvectors of these eigenvalues using you see from linear algebra 1 we know that a v equals to lambda v. Okay, av equals to lambda v. Okay, so we can decide to bring this step to the other side of the equal sign. When we do that, we get av minus lambda v equals to 0. We can factorize v out. When you do that, we get v multiply a minus lambda. But remember, a is a matrix and lambda is what? Scalar. Okay, so we need to introduce our identity matrix. Okay, we can't just subtract the scalar from a matrix. So here we need to introduce our identity matrix. So when we do that, we get lambda I, we get a minus lambda I equals to 0. Okay, then we find where this 0 is a 0 vector and v is a eigenvector. Okay, so when you use this relation, you get the eigenvector of 3 is 2, negative 1. Okay, but when you normalize it, we get what? 2 over root 5, negative 1 over root 5. The eigenvector of negative 7 is also 1, 2. When you normalize it, you get 1 over root 5, 2 over root 5. Okay, so we generate our matrix P. So the first column of P is a normalized eigenvector of this one, and the second column is the normalized eigenvector of what? Negative 7. So we obtain our matrix P. Okay, so now let's diagonalize matrix A. We know that D is given by, we know that D is what? D is P inverse AP. But since A is symmetric, we can rewrite this as P transpose AP. Okay, so when we simplify it, we get this matrix such that the columns, elements in the columns of the diagonalized matrix are the eigenvalues, and the other elements are what? 0. Okay, so now let's change the variable. Okay, so we let x equals to pu. So when you simplify, get u transpose du. Okay, but we know our u to be u1, u2. We know our d to be 3, 0, 0, -7. So therefore u transpose du is given by u1, u transpose du is given by u1, u2 multiplied by matrix d, that's 3, 0, 0 -7, then u1, u2. Okay, so when we simplify this, we get 3u1 squared minus 7u2 squared. Okay, so we have changed the variable from, initially the variable was what, x, and this time around it is what, u. Okay, now let's look at the second part of the question, or let's consider the second part of the question. So when you are given x to be 2, -2, okay, then we know that x is equal to what, pu, and therefore u is the same as p transpose x. Okay, so the transpose of p is this, and then this is x. When you multiply transpose of p by x, we get 6 over root 5 -2 over root 5. So 6 over root 5 is equal to u1, -2 over root 5 equals to u2. Then when we substitute it here, we get 3, then u1 squared, u1 is 6 over root 5, then minus 7 u2 squared. When you simplify this, we get 16. Okay, let's look at this exercise. You can, once again, you can pause this video and try your hands on this question. And this is the question. You make a change of variable x equals pu that transforms the quadratic. So this is the quadratic form, that's 5x1 squared minus 4x1x2 plus 5x2 squared into quadratic form with no cross product term, and hence find the value of q of x when x equals to -2. Okay, so now we have this question. So first of all, we generate our symmetric matrix A from this. So our matrix will be 5. We divide this by 2. That's -2, -2. Then this 5. Then first of all, we find the eigenvalues of A. So the eigenvalues of A can be calculated using this formula. That's the determinant of A minus lambda I is 0. Okay, and this is the same as this. So we find the determinant of this. When you do that, that will be, we get this, that's 5 minus lambda times 5 minus lambda minus 4 equals 0. Then when we expand brackets, we get, when we expand bracket and simplify, we get lambda squared minus 10 lambda plus 21 equals to 0. And we can factorize this completely. When we do that, we get lambda minus 3 times lambda minus 7 equals to 0. Okay, and this is the same as when you find the zeros of lambda minus 3, you get 3. The zeros of lambda minus 7, you get 7. Okay, so we are getting 2 eigenvalues here. Thus they are all positive, and therefore is positive definite. Okay, now let's find the corresponding eigenvectors. So let's consider the first eigenvector. Okay, so when we consider the first eigenvalue, we have lambda 1 equals to 3. Then we let you see the symmetric matrix 2 by 2 matrix, and therefore the vector should be what? 2-dimension. Okay, so we have u1 equals to a1 a2. Therefore, a minus lambda I times v vector v equals to what? A 0 vector. Okay, where our lambda is 3, so we get this. So this is the same as, so subtracting 3 from the elements in the leading diagonals. Okay, so you see we had a to be 5, so this will be 5 minus 3 minus 2 minus 2, then 5 minus 3. Okay, that's why we had this. So we have a1 a2, then we have the 0 vector. So we divide each row by 2. So when you do that, we get this. Okay, also we try to reduce the number of rows. Okay, so we apply the elementary row operation. So we have r2 to what? r2 plus r1. When you do that, we get this. Okay, so therefore from here we multiply this by the vector. So you have a1 minus a2 equals to 0. This means that a1 equals to a2, and we say when you choose a2 to be a free vector, that's you set a2 to be 1, and when a2 is equal to 1, it means that a1 is also equal to 1. To obtain vector v1 to be 1 1. Okay, that's the eigenvector of the eigenvalue positive 3. Now let's move on to the second. Let's look for the second eigenvector. That's the eigenvector of 7. So once again we just subtract 7 from the diagonal elements. Okay, I mean the leading diagonals. So when we do that, we get this, that negative to negative 2, negative to negative 2. We choose our vector v2 to be b1 b2. So from here we can divide 2 by negative 2. When we do that, that will be 1 1 1 1. b1 b2 equals 0 0. Okay, so we apply the elementary row operation. That's r2 onto r2 minus r1. When you simplify, we get this. So now we multiply this by the vector b1 b2. Okay, so when you do that, we have b1 plus b2 equals to 0. Okay, so we let our free vector be 1. That's b2. Sorry. So if b2 is our free vector, it means our b2, we let b2 to be what? Equal to 1. Okay, so we get b1 plus 1 equals to 0, and therefore b1 is also equal to negative 1. Okay, that's why we had this. That's negative 1 1. Therefore our vector v2 is what? Negative 1 1. Now we can generate our matrix P. Okay, and P, I said earlier that the columns of P are what? The normalized eigenvectors of matrix A. Okay, so first eigenvector was 1 1. So when you normalize it, that will be 1 over root 2, 1 over root 2. That's what we have here. Okay, then second eigenvector, that's negative 1 1. When you normalize it, we get negative 1 on root 2 and 1 on root 2. That's what we have here. And therefore the transpose of P is given by this. Okay, so now let's diagonalize matrix A. Okay, so this is given by diagonal matrix D is given by P transpose AP. Okay, and this P transpose, so we have P transpose, we have matrix A, then we have P. Okay, so when you multiply the first two matrices, you see get 1 over root 2 times 5. That's 5 over root 2 minus 2 over root 2, and this 3 over root 2. 1 over root 2 times minus 2, that's minus 2 over root 2, plus 5 over root 2, that's 3 over root 2. This minus 1 over root 2 times 5, that's minus 5 over root 2, minus 2 over root 2, that's minus 7 over root 2. Then minus 1 over root 2 times negative 2 is 2 over root 2 plus 5 over root 2, that's 7 over root 2. Then multiply by p. So when you simplify this, you get 3007. And remember, 3 and 7 are what? The eigenvalues. Okay. Let's continue. Okay, but you see, we were given that x is what equals to pu. Okay, so we let x be x1, x2, and u be what? u1, u2. Okay, then the quadratic form, which is x transpose ax, can be written as this, such that pu is what? Equal to x. So that's pu transpose a pu. And this is the same as u transpose p transpose a pu. But we know that p transpose ap is d. Okay, so we get u transpose du. So we transpose this, we get u1, u2, and this is our d, and this is what? Our u. Okay, so when you simplify this, you get 3u1 squared plus 7u2 squared. That's the first part of the question. We have changed variables. Okay, it was in terms of x1 and x2, and this time around it have been changed to what? u1, u2. Okay, and it have no cross product term. Okay, so when x equals to 2, negative 2, we know that x equals to pu, and therefore when you make u the subject, that will be what? P inverse of x. Okay, and it's the same as p transpose of x. Okay, so therefore our u, which is u1, u2 is given by p transpose, and this is x. Okay, so we multiply, so we have 2 root 2 minus 2 root 2, which is 0, minus 2 root 2 minus 2 root 2, that's minus 4 root 2. So from here we can compare it to that equality of vectors. It means that u1 equals to 0, that's what we have here, and u2 equals to negative 4 over root of 2. And therefore 3u1 squared plus 7u2 squared, so we substitute our values of u1 and u2 into this. So we get 3 times 0 squared plus 7 times the square of negative 4 over root 2 squared. When we do that, we get 7. See, this, the first time gives us 0, and this is what? 16 over 4. Oh, sorry, 16 over 2. Okay, and we know that 16 over 2 is what? 8. And 8 times 7 is what? 52. Sorry, 56. Okay, thanks for watching.